Our next speakers are Dave Fick and Laura Fick. Laura Fick is the head of mixed signal computing and a founding engineer of Mythic. And Mythic is an Austin, Texas-based startup that's creating the next generation of inference microchips. Mythic uses mixed signal computing to achieve 20 to 100x improvements in neural network energy efficiency and performance. And it has raised $55 million from top-tier investors to execute on this vision. Laura earned her PhD from the University of Michigan, and Dave is the CTO and co-founder of Mythic, and he also earned his PhD from University of Michigan. So let's please welcome Laura and Dave.
Thank you, Greg. So feel free to stop us and ask questions throughout the presentation. Let's see. So we're doing an introduction to compute and memory. This is a pretty broad term that covers a variety of technologies, and different people use it in different ways. And today we're using it in effectively the broadest way possible, and we'll jump into different areas of compute and memory. In particular, we'll be talking about what kinds of memories compute and memory can be related to, when it's useful, when it's not useful. We have a few case studies that we're digging into for SSD, and then GPS correlation and neural networks. Then at the end, we'll conclude. So in a nutshell, compute and memory is a broad range of techniques. They have a single underlying principle. Sometimes it's better to create additional compute at the memory than it is to move data from the memory to the main compute. And so there's a major question that has to be answered when you're using compute and memory. What is your performance bottleneck? If data movement in your system is a performance bottleneck, then compute and memory may be the solution for your application. This is particularly important for many of today's applications and post-war design. So we're seeing increasingly large data sets. You can see these petabyte scale systems, and the internet's huge. AI has huge data sets. And the more data we collect, the more data we need to process, the more the memory system becomes a bottleneck. And so compute and memory is designed to address that memory system bottleneck. So when we say in memory for compute and memory, that term is relative. So of course there's memory throughout any system. And so there's a question of which memory are we referring to when we say compute and memory. So here we have a diagram of a relatively standard computing system for general purpose applications. We have a microprocessor which has a CPU and increasingly large levels of cache. We have a DRAM chip or a set of chips that exists off in a separate piece of silicon from the microprocessor. And then we typically have some sort of hard drive like an SSD backing that. And so in these systems, we have a progression in terms of how that memory is accessed. The L1, L2, L3 caches are small and fast near the CPU. Obviously, the L1 is the fastest, and they get increasingly larger, but increasingly slower. The DRAM is huge compared to the chip, the on-chip memory in the cache system, orders of magnitude larger. And then finally, the SSD is again orders of magnitude larger than the DRAM, but is also much slower. So when we have a memory system like this, the CPU typically works directly out of the L1 cache. And the other aspects of the memory system, like the L2 and the L3, the DRAM, these are accessed increasingly and frequently. So the L1 cache is accessed very frequently. L2 cache might be an order of magnitude less frequent. L3 is another order of magnitude less frequent, and so on. So when we say compute and memory, we don't mean the L1 cache, obviously, because that's the memory we're already using for compute. But we could be adding compute to our L2 cache. Instead of transporting data from the L2 cache to the L1, maybe we can do operations directly in the L2 cache. Same with the L3. Similarly, we can do compute directly in the DRAM. So instead of transferring gigabytes of data across this DDR interface, maybe we can do compute directly in the DRAM so we can avoid that data transfer delay. And then finally, the SSD has maybe terabytes of space, and we can do the same thing. Can we add compute directly into the SSD and again avoid this memory system bottleneck getting all the way back to the CPU? So the CPU is very fast, but it has these bottlenecks getting to memory, and we want to try to remove those bottlenecks. Finally, we can also consider accelerators that contain memory. Many of the systems that Mythic makes fall in this class, where we have an accelerator that's designed to be a combination of memory and compute, so that the memory doesn't have to move in order to work directly on it. So this existing memory structure that I discussed is built on a few assumptions. We have temporal locality, which means that when we access a particular memory location, we expect that we likely need to access that memory location again in the near future. So an access once means there's a good chance we're going to access there again soon. Spatial locality is related to that, which says when I access a memory location, I'm likely going to access nearby memory locations relatively soon as well. And finally, there's probability but not certainty. So we don't know exactly what memory locations we're going to be accessing, but we do know probabilistically from temporal locality and spatial locality which ones we're more likely to access and which ones we're less likely to access. So things that we use recently and things near there, we're likely to access. Other things, maybe far away in memory, not so much. So when we describe that access pattern of spatial and temporal locality, we can actually kind of graph that in a way that we can understand visually. And so in this graph, we have frequency of use, so how often do we use it, and then the amount of memory. And so this frequency is going to be on some sort of time scale, say like 1 microsecond or 1 millisecond. And we'll be effectively doing a histogram over that time, so the amount of memory is effectively a histogram. How many pieces of memory did we access a lot, and how many pieces of memory did we access very little? And so we get this big spike where there's a small amount of memory that we access a huge amount. And so we kind of had this small bit of memory that we're working on. We call that our working set. And so you could consider the memory that we access frequently. Maybe we cut it off at this point where the slope is -1. And we call that our working set. And we build our memory system around that working set and making sure that the working set is as fast as possible. And so if we add the sizes to our memory hierarchy to that, we can kind of see that the working set typically exists inside the cache hierarchy, so that very infrequently do we ever need to have the processor access data from DRAM or SSD. And then the DRAM and SSD systems are, of course, much larger. We could consider this log scale on the y-axis. And then the SSD is effectively unlimited in size. So when we are working on our application and we're choosing how we architect that system, we need to consider what is the working set of that memory, or what is the working set of that application, and how can we map that working set to our memory system. So compute and memory applications work with systems that have different access patterns typically, or work with applications that have different access patterns. So you could consider this access pattern where the memory that's being accessed is typically larger in sort of scale than the cache system. So imagine you are working on a sorting algorithm, and in that sorting algorithm you had to keep cycling through your memory, but that memory size that you're cycling through is larger than your cache system. So that means you're forever going to be accessing DRAM in order to run your application, in which case the performance of the application will suffer. And then you can similarly look at what is the size of the memory, or you can consider scenarios where the size of the memory is out to the SSD size. So in these cases where we're seeing sort of this plateau inside of other memory sizes like DRAM or SSD, now we can start considering compute and memory applications. You could also see that if you had a line maybe in the L3 cache instead of all the way down in the L1 cache. There are some other reasons to consider compute in memory. So for one, deterministic data patterns. So for the accelerators that Mythic builds, we actually know exactly what data will need to be accessed and when. And so we can construct our system around that. You might have ASIC capabilities to minimize further data movement. In which case, if you know what your data pattern is going to be, your access pattern, you can actually construct an ASIC to work around that as well, and then really cut down on the amount of data movement. And then finally, we have analog computation, where in extreme cases, we can add analog in a way that almost eliminates data movement entirely. So where compute in memory is not always useful includes general purpose computing. So there needs to be some application that we're targeting with compute in memory. You don't build a system like this in order to take on all problems. You build it to take on a particular problem. You might have a situation with low application importance. So maybe you have an application that you're targeting, but that application is only a small amount of the runtime of the system. That's not a good use of architecting a system when it's only around 90% or 10% of the runtime. If it's more than 90, then you might be able to get a 10x improvement overall for your full application. And then finally, it's not going to work well for small working sets. So typically, if you're looking at compute in memory, you have some sort of situation where the amount of data you're accessing is much larger than the memory near your processor. And so if you don't have a large data set, then you have no reason to add computation to your memory system. So with that, we're going to jump into a couple example applications, and we're going to start with SSDs.
Okay, so we're going to look at a couple specific case studies where people are using compute in memory in their applications to try to see what their working set looks like, whether or not these benefit from compute in memory, and how they architected their solutions to get these advantages. So in this first example, we have a paper by UCSD and Samsung doing in-storage computing on an SSD for a list intersection. So let's take a second to remember that in-memory is a relative term. So we talked about how typically the CPU is working on the L1 cache, but we could do compute in memory in multiple places, the L2 or the L3, the DRAM, and in this case we're looking specifically at doing compute inside of the SSD itself. So in this case study, the authors looked specifically at the application of list intersection. So list intersection is an algorithm that finds the common elements in a set of data. This type of algorithm is very prominent in search engines and analytics queries, where users will type a set of keywords into, say, Google and expect a list of web pages that are relevant to those searches to come back. This means that the algorithm can be operating on a massive amount of data. The speed of this algorithm is dependent on many different parameters, how the algorithm is implemented, the list length, and the correlation of that data. So the question we want to ask here is the data usage requirements for this specific application amenable to compute in memory techniques? So let's start by looking at the architecture of an SSD in general. So modern SSDs are typically architected with higher internal bandwidth than the host interface bandwidth, sometimes like 2 to 4x increase. This is beneficial for compute in memory techniques because if your host bandwidth is the same or even faster than your internal bandwidth, then you are not going to benefit as much because it might be just as fast to move the data to your host and compute on your host CPU. So in this case, though, with the SSD, the authors are using the SSD controller as an offload engine to execute some programs directly next to the memory that they're using. And they're doing this through the use of a Samsung Smart SSD. And so the difference here with the Smart SSD is that they've added a layer of firmware basically in their SSD architecture in order to very efficiently run these algorithms. So how does the Smart SSD interact with the host in this system. So the host system in this case is sending only metadata to the smart SSD. So this is addresses and lengths of lists. And the SSD contains all of the load lists that they're comparing against, all of this data that you need to generate your feedback, which is like basically every website if you're trying to search these, or the lists for every website. And then they're also going to perform the list intersection algorithm on the SSD itself. And the big benefit here is a lot less data traffic. If you're constantly reading these load lists from your SSD to your host CPU, that's a huge memory bottleneck. And so all they send back to the host system is the results of this specific intersection query. So something else that they looked at is the effects of their architecture on the performance of the system itself. So in this particular experiment, they're comparing their smart SSD implementation against a regular SSD. And in this case, they performed compute in memory on both systems, but the smart SSD is architected to more efficiently run this algorithm. And so what they're showing here is that the smart SSD has capabilities that at some point let it become much more efficient than using the regular SSD. But in some cases, it's more inefficient. So here they're sweeping the entry size for their list intersection algorithm, which is basically modulating how much data they can skip when they're doing this comparison. So at a value of 4 for the entry size, they're basically reading in all of their data. And because of the way this Samsung Smart SSD is architected, they have to read that into a local cache, which becomes the dominant source of both execution time and energy. Now, at some point, around maybe 256 bytes of entry size, they get a huge improvement in both execution time and energy compared to the regular SSD implementation. So we can see that in addition to choosing a correct application for compute and memory, the way that you architect your system can have a huge effect on the performance that you're getting. So let's just discuss a little bit more about the access pattern that they're looking at here. So uniform workload for compute and memory is definitely better. So we want to know that we're accessing a certain amount of data many, many times. And that is definitely what they're doing with list intersection. You have to load all of these lists that you've stored on your SSD every time you want to do this comparison. So we are consistently accessing a large set of data, large enough that it needs to be stored on an SSD in this case. Another thing to keep in mind, though, is that a larger amount of data is also better. So even if your workload looks similar, and you have a flat line down in your L2 or your L1 cache, that might not benefit as much from compute and memory because you're right next to your CPU anyway. So you get a larger benefit if you take the bottleneck of coming from your SSD onto your host because you're operating on so much memory for a consistent amount of time. So in this case, they fit both requirements. They have a significant amount of memory that they're consistently accessing, so they can see big improvements by using a compute and memory technique in their SSD. So the next example we're going to look at is a GPS accelerator that uses compute and memory with analog compute. This is a project done by Mythic, formerly known as CICC, in conjunction with the University of Michigan. So let's start by looking at what is a GPS algorithm that we're trying to accelerate here. So GPS is a 4-dimensional search. We need to find our coordinates x, y, and z, as well as some time offset t. It's calculated by acquiring time offset from 4 or more satellites, and it's sent as a CDMA signal, so it's received well below the thermal noise floor. So how do we actually acquire this signal? We're basically doing a lot of comparisons between our GPS signal and a stored reference pattern. We're trying to do a time domain search by shifting through this signal and comparing at each time point to see what the correlation value is between these two signals. So that means whenever we're doing a correlation for a GPS signal, we need to do thousands of 2-bit vector multiplies and thousands of accumulate operations at each time point. So we're just going to shift this signal by one time step and do all multiple thousands of these calculations again. This is extremely compute intense, The pattern is very long in order to reject noise and increase gain of the system. So what does this mean for a GPS application? This requires many, many operations, like I said, 10 to the 9 just for civilian GPS, and if you're looking at military-grade GPS, that's orders of magnitude more calculations. This makes this application very energy and time intensive, taking between 10 to 350 milliseconds per satellite to compute. So in this example, we chose to use analog compute as the solution to solving this problem. So analog compute can mean a lot of different things. You could do analog compute on capacitors by summing or storing charge. You can do compute using transistors by modulating threshold voltage to change conductance. And you can do compute using current sources that are digitally controlled. So in this particular example, we chose to use current sources. What we want out of this is digitally controlled current signals that can sum together. That's going to give us our 2-bit vector multiply and accumulate. The benefits here are that we get natural summation from our current sources if we share a common wire. That's just Kirchhoff's current law. And another advantage is that we can tolerate using many inputs with a very process-tolerant design. So current sources have a lot of benefits in terms of process mismatch. So if we tried to do this application in a fully digital design, what would that look like? Well, we need 4,096 2-bit numbers that we have to add together. We'll first multiply and then add together all of these multiplications. So in a digital system, that looks like over 8,000 full adders in a 15-stage tree. And this is going to scale with the number of inputs. So if we choose to increase our number of GPS inputs, this is going to get proportionally larger. Now, what if we implement this using analog compute in our current summing technique? So now we have 4,096 logic cells. In order to do 2-bit multiplication, each of these cells has 3 current sources. And these current sources produce some current that is proportional to our digital input and the current source value itself, which is pre-programmed. These current sources sum together along a common shared summation wire, and the combined output current is equal to the multiplication and summation of all of our vectors and cells. And so we're actually doing compute in memory here as well, because we've stored our reference pattern inside of our current source cell. So here we have both analog compute and compute in memory combined together. Another benefit here is that because we have single wire summation, this approach looks fairly similar for even a much larger number of input signals. So in order to add another input signal, we add one more cell here and have one wire. So our wiring doesn't blow up when we add another input signal. So we have a lot of advantages from analog compute, but we also need to address some disadvantages or problems, right? Analog compute can be very efficient, but it can be noisy. So that is the downside from using analog compared to digital. So you don't want to use analog compute for any application that you might have. But in terms of GPS, it actually is fairly beneficial and relatively, well, it still has noise, but the noise comparison isn't that bad. The benefit here is that noise is effectively decreasing as our number of input terms increases. So we get some square law averaging that happens in this calculation. And our GPS signal has a lot of input terms. 4,096 is enough. The other problem that we had in this project was that our correlation range is actually pretty small. We're typically not looking at 0 to 100% correlation in these signals. It's somewhere between 48 to 52%, which means that our LSB size is actually 0.5% of this signal. So we did have to heavily optimize our circuits to work well in this small range. So I'm going to go through how our analog calculation chain works here. So on the left, we have all of our current cells. So that's 4,096 cells times 3 for each current source, so around 12,000 current steering sources. This has our pattern stored next to the current cells, and it takes the GPS signal in. These currents are summed along 2 different wires, positive and negative. And then we have a couple amplifiers that control the voltages in this circuit. So one common mode amplifier to set the common mode voltage equal to Vref in the system, and one equalizing amplifier. The goal of this amplifier is to drive these 2 shared nodes together to equal Vref. And it does that by generating a differential voltage on the output that is representative of the amount of current in the system, and therefore representative of our GPS correlation signal. This is sampled and sent into a 3-bit flash ADC for digitization. So in the initial state, we can assume that our system is set to Vref. The equalizing amplifier is in a steady state. And then we're going to shift in a data signal from the GPS satellites. So at the time the pattern shifts, the current in all of our cells is going to spike and settle back down to Vref based on the settling time of the equalizing amplifier. At the same time, and because of this, we are generating a differential output voltage on this same amplifier that is sent into our 3-bit ADC. If we flip the signals in the opposite direction, this is going to work the same way. The amplifier is going to drive our current summation lines together, generate an output voltage that we can digitize. And so these are some examples for the large-scale application, large-scale outputs. So 48.5%, 51.5%, and then if we're looking at a totally uncorrelated signal, around 50%, we're going to get less of a spike, still going to settle to the same value, and our output voltage is going to be around 0. So what does this look like on chip? We have our analog chain shared between all 4,096 cells. Each of these cells, I said, has 3 current sources, and memory that stores our reference pattern inside of those cells. Each of these blocks has a common current summing line that all are shared together at the analog input chain, and this is used to generate our output voltage. This is frozen. It's completely black.
Wait for it or... Sorry about this. Sorry, what slide are you on? 47.
Okay, so what does this look like at the output? So here we're comparing our measured analog results that are digitized by our 3-bit ADC. This is from our chip, compared to an ideal digital simulation. So this digital sim is not 3 bits. You can see it has a finer resolution than that. And it's perfectly ideal. So this is a single pass through the matched filter with 4,096 correlation calculations. And what we're trying to look at here is, how much error are we getting from using analog compute? The basic look here is that these are pretty much identical, and we can do further analysis to see how much is lost. Most of this is through quantization. So you could get a pretty similar result if you used a digital system that was also 3 bits. So this is measured at 170 megahertz, and what we look at next is how much of our noise is coming from our analog compute compared to other parts of the system. So we do need to take into account other noise factors that might swamp out any issues that are actually caused by the analog compute itself. So first, we have to keep in mind that the signal is going to have some inherent noise. There's an RF front end that introduces some noise to the system. This is common between an analog compute system and a digital architecture. And then finally, we look at the analog compute noise normalized against the quantization noise. So if a 3-bit digital accuracy in your system is tolerable, then the amount of noise compared to that caused by cell current variation versus, sorry, I can't see my pointer. Cell current variation versus the actual analog chain noise is actually pretty low, around 10 times lower than just quantization noise, which you're going to get if you quantize a digital value to 3 bits anyway. So here we are still dominated outside of that by cell current variation, which is around 0.1 compared to the quantization noise. But what kind of impact can using analog and computed memory make to this system? So, compared to other digital works that perform similar GPS calculations, we're seeing a 340 to 27,000 times performance increase at a 67x energy efficiency increase. And one of the big benefits that we're getting here is scalability too. So if we want to increase the number of terms, like we said, our system doesn't look significantly different than it currently does now. We do have to increase the number of current cells, but we can still share the common current summation wire. And so in conclusion, we were able to implement this GPS system using compute and memory. The reason why we were able to get such big benefits from using a compute and memory technique is because of the workload that we observed before starting this project. So we know that we have a fixed set of memory that we are going to use every single time we do a GPS calculation. So this isn't a variable set of memory. It is still fairly large. And if we can do analog compute and memory next to this memory storage, we can see a pretty big energy and performance benefit. Okay.
All right. For our next example, I'll be talking through Mythic's core technology, where we use analog compute and compute in memory for neural network applications, particularly for AI inference applications. So deep neural networks are basically the hottest trend right now in artificial intelligence, and they're largely these multiply accumulate operations. These are the same operations that we saw for our GPS technology, where we have two signals that we're multiplying together. One signal that's a code pattern, and one signal that's measured from a satellite. Deep neural networks use a similar pattern, except that instead of multiplying by a single signal, we multiply by a set of them. So we have our input data, which is going to be represented by a vector. We have our neuron weights, where each neuron is one of these columns. We multiply this vector by the matrix, and we get an output vector. This is similar, if we were to compare it to GPS, it's the same idea, except these weights here are, we have multiple columns. In GPS, we had a single column that we're just reaccessing very rapidly, so checking different time steps. In this case, we have different neurons. So in both of these applications, we have this key operation called the multiply accumulate, or MAC, which is typically low precision. So in modern inference applications, this is typically 8 bits. So it would be multiplying two 8-bit numbers together and then adding these different terms together, which can range in the hundreds or thousands of terms. So a figure of merit that we need to consider is how many picojoules does it take to execute a MAC operation. So in this system, when we're looking at our weights, we're looking at our data access, we've got two different types of data. We have our weight data and we have our intermediate data. So if you remember back to that graph where we have our memory access patterns, our weight data is extremely bulky. and we're actually going to access it in a round-robin pattern. The input data is relatively small in scale, and then we're going to access it very rapidly. So we'll access it a few times to multiply by this weight data, and then we'll generate these outputs, which becomes our input data to the next layer. And so this pattern here might be replicated, say, 50 or 100 times in a row. So if we look at a 1,000 input, 1,000 neuron matrix, we see a pretty big difference in how these types of numbers are accessed between the weight data and the inference data, or the intermediate data. So the intermediate data has this property where the data accesses are naturally amortized. So remember, we're talking about picojoules per Mac as our figure of merit for the system. And if we look at one of these inputs, x0, we have to access that from memory. So anytime we're accessing a piece of data, we have to be accessing like an SRAM. The data has to be coming over some interconnect, and then it's getting to the processing unit. So in this case, when we access x0 from our memory, it's actually being used for multiple Mac operations. And in this example, we said there's 1,000 of them. So x0 gets amortized by a factor of 1,000. So imagine that we're accessing x0 from a SRAM. If it costs a picojoule of energy to read that SRAM, then once we amortize it across all these Macs, then it only costs us 1 femtojoule of energy per Mac in order to access x0. So this amortization of the intermediate data means that we don't really need to worry about the intermediate data too much from a figure of merit point of view. The weight data, on the other hand, doesn't have that same amortization property. So each of the weights inside this weight matrix are only accessed once. So if you look in the equations over here, A0 only appears one time. So if it costs us a picojoule to access A0, then our Macs have our picojoules per Mac has a floor of at least a picojoule, because right off the bat we have to pay for accessing A0. Worse, this weight data is very large. So in many cases, it's on the order of tens of megabytes, and so that won't fit on chip in many applications or in many systems, so we have to store it in DRAM. So not only do we not get to amortize that data, it's a very large amount of data, so we have to pay lots of energy in order to store it and in order to access it again and bring it back over the interconnect, maybe over a PCB in order to get access to it. So for this reason, deep neural networks are all about weight memory. So when you're architecting a system for working with deep neural networks, it's entirely about how do you store that weight memory, how do you access it, how do you ensure that you don't use more storage than you need to. And some of these numbers help illustrate that. So these are some of the key applications that you see in this space. AlexNet and VGG are more historical than actually used in practice. ResNet 50 and OpenPose are applications that we see many of our customers using today. So when you look at the number of weights for these systems, you can see that the weights range in the tens, in the VGG case, hundreds of millions. Even if we take only 1 byte to store each weight, we're still spending many megabytes or tens of megabytes to store it. Additionally, the number of Macs, or the number of multiply accumulate operations that we're performing, number in the billions. Especially for OpenPose, you can see 180 billion operations, and this is per frame. And so when you multiply it up by 30 frames per second, let's say you're doing a video, now you're getting into the hundreds of billions or maybe trillions of operations per second. So I had like a little 1 next to all these applications here. That's because the numbers are actually for 224 by 224 resolution. And most security cameras these days are about 1080p. 1080p is good for low light imaging. You also see some 4K for areas where you see better lighting conditions. So if you're running 1080p, that's about 20 times more processing needed to run than 224 by 224. And so you can imagine for, say, ResNet 50, instead of running 105 billion max per second, in order to run 1080p, we need about 2 teramex per second. So 20 times more compute than that. So now we have tens of millions of parameters to store. We have many tens of billions of data accesses to perform, maybe hundreds of billions. And so there's a question of how do we achieve high energy efficiency, high performance, and say an edge power budget, for example, 5 watts. In many systems, and many applications like cameras, for instance, if you're doing a security camera, the device, even if it's connected to the wall, can't radiate more than about 5 watts of power. If you own a Nest Cam or a Drop Cam and you ever touch it, you'll find that it's hot to the touch because it has to radiate that heat all through its plastic or aluminum casing. And so we can't spend 100 watts of GPU in the system in order to add intelligence. These weights in particular are very difficult to store in an edge solution. So if you look at, say, an SoC typically used in like a Nest Cam, they might have 3 megabytes worth of on-chip memory. You can't fit 23 megabytes worth of weight data. So there's been a lot of techniques that have been invented to address this weight energy consumption issue. There is weight reuse. So there's 2 different flavors of that. You can focus on using convolutional neural networks, where we reuse weights for multiple windows. And we can build specialized structures to work with that, like systolic arrays, which is another type of compute and memory structure. So now all problems map well to convolutional neural networks. And so you'll see them used quite heavily for image recognition. But then once you get into, say, object detection or things like open pose, you don't have quite as much convolution as you did earlier in the network. And so convolution really hinges on an invariant that you're adding to the problem, where you're saying, if I take this operation, I can translate it to different parts of the image. And that's not true for all types of neural network processing. You can also focus on large batch sizes. So when we say batch, that means that you're running one or more, or you're running more than one input at a time. So instead of processing 1 video stream, you're processing 2 or 16 video streams in parallel. And you can get additional memory access benefits from that, where when you read that piece of weight data, you're not just using it in one place, you're using it for each of your batches. And so that can be very powerful in an enterprise environment, but often in an edge case, you can only have a batch of 1. Let's say you're in that Nest Cam, you only have 1 video stream that you're processing at a time. So there's no way to do batching in that case. And even if you could, you're limited to 5 watts, so it doesn't help you to be more energy efficient if you're still going to increase the amount of power that you draw. This also has the disadvantage of increasing latency. And so this is not, in many cases, this is not the best strategy for a system. The other major axis that we can look at is weight reduction. So we can shrink the model. This can be done by using a smaller network. SqueezeNet out of Berkeley is very famous for that. And the idea is we're going to just take as small of a network as we can and cram a network or cram an application onto it. The disadvantage of this is in many cases you're reducing the capability. So SqueezeNet doesn't perform as well as, say, ResNet 50. It doesn't have the same accuracy. You can compress the model. This is very common if you read circuits papers on neural networks. You can increase sparsity in order to eliminate many of the parameters. I've seen as high or as 99%, and in which case you're only doing 1% of the work but taking credit for 100% of it. Or you can use literal compression, and there's ways of taking a sparse matrix and forcing a compression pattern on that in order to get more efficient packing out of the system. And finally, you can reduce your weight precision. This is the most common one, where you replace a 32-bit floating point number with maybe 2 to 8-bit integers. And so 8-bit integers become the de facto gold standard in inference computing, even in enterprise systems, because the amount of power they draw from the wall typically is the dominant factor in the cost of operating that system. Again, this can possibly reduce your capability depending on how aggressive you are. Typically around 8 bits you're okay, but if you start degrading much more, down to like 2 bits, you're certainly going to lose accuracy. So when you're architecting a system to run neural network inference, there's a question: do you use DRAM or not use DRAM in order to architect this system? And so the DRAM has a benefit that you can fit arbitrarily large models on it. You don't have to worry, will this network fit on my chip? Every network will fit if you have a gigabyte of DRAM sitting next to it. You also don't need as much SRAM on chip, so you can save money in terms of die area in the silicon. So if you look at, say, the neural network accelerators in a typical SoC, it's only a very small piece of die area with a very large amount of peak performance. And that's because you don't need to pack as much memory directly in the system when you're backed by DRAM. So there's some drawbacks to DRAM, though. One, typically, there's a huge energy cost for reading weights. Every time you have to go to DRAM to get weights, you're going to be paying a very large penalty. There's limited bandwidth for getting to weight data. So depending on how aggressive your DDR interface is, you might have a very narrow pipe getting to DRAM relative to the on-chip memory performance that you might have. And then finally, your energy efficiency and performance is going to become highly variable compared depending on your application. So if your application fits entirely on-chip, you'll get very high performance, very high energy efficiency. But if you have to go to DRAM, the more you go to DRAM, the more penalties you're going to pay for energy and for performance. And so when you architect the system using DRAM, your customers will not have as much advanced knowledge about what their application performance will be until they actually work with your product. So if we look at common neural network accelerator designs, they typically fall into 4 categories with 2 axes. One axis is enterprise versus edge, and the other axis is DRAM or no DRAM. So in the case where you have, let's start with enterprise, typically these are reticle-sized chips, so they're going to have a huge amount of on-chip memory. In order to support that, though, they need to take on tens of watts of power. So you typically see 70 plus watts. They can be very light in sparsity, and they can support a variety of precisions. And so because of that, they're able to get great accuracy. And since they're reticle size, they can get very high performance. Now you'll see a huge jump, though, going from DRAM-based systems to systems that don't require a DRAM. And that's because these no DRAM systems are limited in the size of the application that they can fit on chip, but then they never have to pay the energy penalty for going off chip, and they don't have to pay as much transport on chip for that memory as well. In the edge case, edge typically has much smaller dies. You can't have huge amounts of memory, so there'll only be a few megabytes of SRAM. Because of that, edge systems are going to be very heavily dependent on DRAM. The power needs to be very low, so we're talking 5 watts or less. To compensate for all of these restrictions, these systems use either moderate or heavy sparsity in order to achieve their power goals. Because of that, the accuracy and performance will be poor. So typically the performance, from what I've seen, you'll get maybe 200 by 200 resolution running at 5 frames per second. So nowhere near the 30 frames per second and nowhere near 1080p that system builders are looking for. The energy efficiency will be typically better than the enterprise system with DRAM, but it won't be as good as, say, the enterprise system without DRAM because they don't have all those amortization techniques that the no DRAM enterprise system is able to take on. So Mythic adds this new category for using its analog compute. So we have now, instead of DRAM or no DRAM, we have an NVM technology. So the amount of SRAM on our system is still pretty small, less than 5 megabytes. And the power is still going to be small, less than 5 watts. But we can do things that other systems can't. So we can have no sparsity at all. You'll see why we don't need sparsity later on. We are supporting a variety of precisions from 1 to 8 bits. We don't support floating point at this time, but we found that that's not really needed. The accuracy under this system is excellent because we don't have sparsity and we can run with 8-bit precision. And we can still maintain high performance due to the highly parallel aspects of our system. Finally, the energy efficiency that we have is best out of all of these different categories by a pretty large margin. Additionally, Mythic can do this in a 40 nanometer process. So we're actually using a 40 nanometer LP process. So most of our power is actually dynamic energy, and LP processes are not the best for dynamic energy. And the systems that we're comparing to here are on like the 7 to 16, maybe 22 nanometer process. And so we actually have a lot of life left in process scaling. It's kind of like a reset of Moore's law, because our next generation can go to 28 or 22, and then we can be looking at 14, and so on. This chip operates as a PCI Express accelerator. And so we have this input-output relationship with a host SoC. So let's say we're running image recognition where we're labeling an image. That image will be sent as a data packet over to the Mythic IPU, that stands for Intelligence Processing Unit. The IPU will be running an inference model. It's programmed a lot like an FPGA, where it has a firmware that's loaded that contains the application. And it's going to run inference on that piece of data and then send those results back over the PCI Express port. The host SoC runs the operating system, manages these different interfaces like Wi-Fi and the camera. It runs the applications that the users might be accessing. And then, of course, it has the Mythic driver in order to access this interface. Mythic also supports multiple IPUs. So some applications require a lot of performance. Maybe you want to run 4K instead of 1080p, in which case you might need more than one IPU in order to support that level of performance. This is possible by managing through this PCI Express interface across multiple devices. And they can also talk to each other through PCI Express as well for direct data transfers. So Mythic makes this happen by introducing something called a matrix multiplying memory. And as I talked about earlier, when we talk about memory-dominated systems, all of the energy costs are in memory access and memory transport. So if we're going to read memory out of a memory array, we have to swing those bit lines. And once we've done that, we need to transport that data to the processor. And so Mythic is going to eliminate both of those by not reading the weights in the first place. This makes weight memory access effectively energy free. We're only paying for the multiply accumulate operation itself. And we also eliminate the need for batch one or batch more than one. So this means that we can process a single data stream at a time at maximum efficiency. We do not need a convolutional neural network focus. We can run recurrent neural networks or dense neural networks with the same efficiency. We don't need sparsity or compression. We have a full memory array here, so if you eliminate numbers from it, it doesn't really help you. And then we remove the need for NeRF DNM models. So we don't need the smaller compressed neural networks. We can work with full-size neural networks like ResNet 50. So let's revisit the matrix multiply. So we have our primary calculation where we're doing our input vector times the weight matrix. This is going to give us an output vector. So you can see it here. So here's our input vector, our weight matrix, and then our output vector with the equations with all the different max. So to use our matrix multiplying memory, we're going to replace this neuron weight matrix with flash transistors. So remember earlier I said that accessing this memory was not going to be amortized the same way as our input data was. So the intermediate data. So this is already fairly cheap to access. This is expensive to access, so this is the one we're targeting with the matrix multiplying memory. So we're going to use analog compute in this case. And the way we do that is we use our flash transistors as variable resistors, where the resistance value, or conductance value if you want to think about it that way, represents the weights. So we have our grid of flash transistors here, each represented by a resistor. This also means that we can use future non-volatile memories as well, like DRAM or PCM or carbon nanotube memory, as they become qualified and available. Today, flash transistors are qualified and available, so that's what we use. We're going to use the V equals IR current equation to get the math that we need. So basically, the current that we're getting here, I, is going to be equal to V over R, or V times conductance. So our input is going to be the V. We're going to take our input X, run it through a digital to analog converter, and that's going to generate our voltages. And this voltage will be a voltage across the resistor. So that's going to be our input number. Our weight is going to be the conductance or resistance of the flash transistor. And so the input voltage times the conductance is going to give us a current. And that current is now going to sum on the bit lines naturally. So we don't actually have to add anything together. The current just kind of lines right up, and we run it through this ADC. In this case, it's going to convert a current back to a digital value. So our system is actually entirely digital. So all of our interfaces to this memory array are digital. And then the bit cells here are going to be analog, and the currents inside are analog. So if we take this, if you imagine this setup here, you can relate it back to these equations where this is our column. So our column of flash transistors here is now going to be reading all of these numbers multiplied by those numbers. The way this is designed is we actually get a commercial off-the-shelf flash memory array or other non-volatile memory array. We get a full example, so it's typically designed to store 1-bit digital values. And we get a license to modify it. So we'll strip off all of the peripherals, so we don't need the input drivers anymore and the decoder structure. And we don't need the sense amps that existed there before either. So we strip those all off, and then our analog designers design DACs to drive the inputs and ADCs to read the outputs. So the memory array itself is unchanged. We don't mess with the bit cell. We don't mess with like all the wiring and other structures around the bit cell. But we do replace the peripherals entirely with these analog peripherals. The digital top-level architecture is very important for this application. Analog compute and memory is very powerful, but there's certain things analog doesn't do very well. So it doesn't do interconnect very well, and it doesn't do intermediate data storage very well. So we do these things in digital. So for interconnect, we use a network on chip, which I'll show in a later slide, and we use SRAM as our intermediate data storage. Between these two things, our system is able to have a huge amount of programmability. So if we did an all-analog system, it'd be very difficult to have a flexible top-level architecture that allows our customers to run a variety of applications. But by having a flexible top-level digital system, we're able to look like a fully digital system with the flexibility of a fully digital system. To simplify our time to market, or to improve our time to market, we actually use digital approximation in this first generation of the system. So instead of using a DAC here, we use a way of a digital approximation. So we're able to achieve the same result as we would with our analog, and this also means that we have a clear place for future improvement. As we go and replace this in the future with the DAC, we'll actually get a 4x improvement in performance and energy efficiency over what we have today. So if you break down the system energy consumption, we were looking at a standard application for ResNet 50, running a batch size of 1. And we picked this as a representative application because most of our customers are interested in this one in particular. However, our system is application agnostic, and the energy efficiency doesn't vary that much depending on application, unless you have some sort of like worst case scenario type application. So if you look at our pie chart here, the analog compute ends up being about half the energy consumption of the system. And then the digital storage, so this is SRAM, is about 0.1. The control logic is 0.05, and the PCI Express is 0.1. So these numbers are out of 0.5 picojoules per mech. So this is sort of the thing that really matters to customers. They're like, okay, interesting floor plans and pie charts and all that stuff, but what does this really mean? So here's a comparison against a high-performance GPU and a high-performance SoC on frame rate and power draw for ResNet 50. So this high-performance GPU is about $1,000, and it can run about 900 frames per second. A lot of times what happens is our customers will develop on one of these GPUs, and then they'll go and try to deploy on an SoC. What they'll have happen is their performance will crater because a little tiny SoC SIMD unit is not going to keep up with the full-fledged GPU. The reason why they do that, though, is because they can't draw 167 watts inside of something like a camera system, but they can draw, say, half a watt. What we provide, though, is the ability to run the full application. So we have the same performance as that GPU, but we're only drawing, say, 2 watts of power in this example. So this is very important because when our customers run into this performance crater, many times what they do is they end up stripping away their application. They start removing features, they reduce the resolution, they reduce the frame rate, and then suddenly the promise of AI went away. AI was promised to be amazing, but then when you try to go and deploy it in real systems and the performance craters, you're no longer achieving what you claimed from the outset. And so we get to that trough of disillusionment. So we're able to provide this GPU performance in an edge form factor. Another application is OpenPose. So this is OpenPose is an application that estimates the pose of a person. So like how are they standing? Where it's important is when you're trying to estimate what the person's doing. So you're not trying to just figure out like a stick figure for them, you're trying to figure out what is the action that person's taking. So for example, if you're doing a self-driving car or driver assistance for a vehicle, you want to recognize a person that's standing next to the street as different from somebody running into the street or walking into the street. Similarly, if you're doing a security system, you might use the pose to estimate whether or not a person is doing something that's harmful to the environment. So are they attacking someone? Are they breaking something? And so this is a very powerful tool when you have a camera system that's interacting with people, because now you can start to understand what the person's doing. So in this case, our architecture is actually able to outperform the GPU, and the reason for that is because the GPU needs to rely very heavily on DRAM to the point that it degrades the applications beyond our performance. So we're able to outperform GPU. SoC is not even useful at all in this space, less than 1 frame per second. And again, this isn't even 1080p resolution. For performance, again, the GPU is drawing quite a bit of power, and our system is able to draw only 5 watts in this case while having excessive performance. You don't even need 105 frames per second. Looking at the digital architecture again, I'm going to show you how the system's composed. So it's actually a tile-based design. We like tile-based designs because you can kind of construct them like Legos. If you have different types of, if you have different Legos, you can put them together in different and interesting ways. In this system, our key Lego is this matrix multiplying Lego, where we have our matrix multiplying memory, which has our weight storage. These are the flash transistors. And we have our DACs and ADCs, which are the peripheral circuits of the memory array. On the digital side, we have our SRAM for intermediate data storage. We have a SIMD unit for providing operations that our matrix multiplying memory is not able to take on. And then we have a network on chip router to provide the interconnect to adjacent tiles. There's a RISC-V processor. This doesn't actually process any of the data. It's entirely used for synchronization and control. The network on chip router connects to adjacent tiles. So it's in a grid topology. And we'll have many of these tiles in a system. This is actually a pretty big system with this many tiles. Each memory here stores about 1 million weights. So a typical product system would have between 50 and 100 tiles. We can, like I mentioned earlier, it's programmed much like an FPGA. So there can be different applications mapped to the system. So in this case, we have scene segmentation occupying this region. We have camera enhancement in this region. We have object tracking in this region. Just 1 second. So, as an overview of the system, our initial product that we're targeting will be a 50 or possibly 100 million weight system. We have a PCI Express port on the periphery. This is actually 2 tiles on the edge as opposed to like a separate block like this. And this provides about 20 gigabits of performance. So we can carry 4K video over this PCI Express port for processing on chip. We also have a basic control processor. So the thing that the host SoC interacts with is a processing system, and we're using another RISC-V core for this control processor. This Gen 1 architecture can go up to 250 million weights. Actually, I think when I recalculated this recently, we got up to about 400 million weights if we did a reticle size system. We can add more PCI Express ports. We can add USB 3. We can add direct audio or video interfaces. Imagine the camera chip could talk directly to this chip, and it'll do all the camera enhancement and object tracking directly in stream before it even gets to the SoC. And then this chip would connect to the SoC either using another MIPI CSI interface or possibly PCI Express. And then finally, we could add maybe an ARM subsystem on the chip, so we could be the SoC ourselves. So wrapping up here. So in review, there's a question of what is possible with compute and memory. So this, again, is a range of systems having compute that's in the same package as the memory system, or having compute directly inside the memory array itself. There's a wide range of applications or styles. But typically, you're looking for at least a 10x improvement in energy efficiency. So in many of the ones that we showed today, you have over 100x. And then a greater than 10x improvement in performance. So you're no longer you've eliminated that memory bottleneck. So now, what kind of performance can you achieve without that memory bottleneck? There's some application-specific benefits, but not every algorithm can see a benefit from compute and memory. So some will benefit more than others. So any sort of memory-heavy applications where the memory is being accessed typically in a round-robin pattern, that's where you're going to see the biggest improvement. When you're considering compute and memory, there's a couple questions about what the data set looks like. Is it a wide data set? So that means you have when you're talking about that image and you see something that's very wide, that means there's a group of memory that's being accessed very frequently, a large group of memory being accessed frequently. And then how large is that group? So do you have a chunk of memory that's being accessed in, say, like a round-robin pattern that's bigger than DRAM or bigger than your local cache? That's a good target for compute memory. How important is this algorithm to our system? So is there an algorithm that we can accelerate that takes up 90% of the system resources or more? And then finally, how predictable are our data patterns? So if we know that we're accessing in a particular order, like round robin, then we can take advantage of that, make some big energy efficiency improvements. And that also allows us to reduce our data movement and free up the other parts of the memory system. So one of the things I forgot to mention was that when you offload these applications from your main processor to compute memory, that also means you're freeing up that memory system to take on other applications. So in the case of the SOC, when we offload AI from the SOC to our analog inference accelerator, now that SOC has more bandwidth to its DRAM to run other applications. So it's more than just running this application faster, it's freeing up the main processor. So this is our final slide, so we'd be very happy to take any questions.
From 0 to 1,000 continuously you can store the data. Equivalently, you can store some discrete.
So I think you asked how many levels can the flash hold? So our flash memory can store 256 levels. And so the question is, how is that possible when the original memory was binary? And the reason why that it's possible is because the memory storage requirements are very different for compute and memory than they are for a typical digital flash storage system. So when we get that IP off the shelf, the requirement that they're holding to is they can store that data for 10 years after cycling 10,000 times.
When you program the flash data, you have to apply some current voltage. So can you control the 256 level?
Yeah, so you're asking how do we precisely program the flash cells to 256 levels? Yes, so we do control that through doing like an iterative programming process. So you can program a little bit, read, program a little bit, read, and you can set that pretty accurately.
So what kind of ADC do you use to convert
Yeah. So yeah, we can't give details of the type of ADC that we use. Yeah, so we use an 8-bit ADC. Mm-hmm. Yes.
Thank you for explain the area efficiency of embedded flash, like compared to the on-chip memory.
So he asked, can I discuss the area efficiency of embedded flash versus SRAM? Is that right?
Yes.
So I would say that the embedded flash is a little bit more dense. So the advantages of embedded flash are that we're able to use 2T cell to store 256 levels. If you're using, say, 6T SRAM, in order to store an 8-bit value, you need 48 transistors. So the advantage for the flash is that it can be very dense on a cell basis. The disadvantage is the analog compute, the ADCs and DACs actually take up a fair amount of area. So if you can make your array structure very large, you get very good area efficiency. But if you wanted smaller arrays, the area of the peripherals dominates very quickly.
Analog computation in advanced technology still durable for representations. So you're mentioning that you adding current in Intel. So if
So he's asking, as we go to smaller nodes where leakage might be higher and maybe variations higher as well, is analog compute still going to be effective? And the answer to that is yes. So the techniques that we've developed for analog compute cancel leakage and they cancel process variation. So actually, right now for our ADC, a third of the cycles are spent on calibration, just to eliminate those sorts of process variations. We also run a differential processing scheme, kind of like the GPS application that is fully differential. So any leakage in that case is canceled.
When you do the CRM, you do layer by layer, say especially in DNA.
Yeah, so he asked when we run compute in memory, do we run layer by layer? And let me find the right diagram.
So the question comes is when you there is still latencies between so you do the interface between the two layers.
Yes, so there.
How do you avoid that?
So the question is, how do we handle latency between layers? And so the way this operates is a neural network layer will be resident in one of these tiles, and the next layer might be on, say, the next tile. And so if you had, let's say you're running ResNet 152, you might imagine layer 1's in the first tile, layer 2's in the second, and so on. So the application kind of snakes its way through the chip. Each of those steps has some latency to it. The 80s, as you're working your way through the compute memory, that's going to take some time to load up the inputs to the DAC. It takes time to run the ADC, and it takes time to transport to the next SRAM, and so on. And so when we operate the system, we actually use effectively work queues inside the system. So you can imagine between each neural network layer, there's a FIFO, and there's something reading that FIFO and something writing the FIFO. And so usually for neural networks, there's enough work to be done that you can keep those FIFOs full. And it's not really a latency-bound application, it's more of a throughput-bound application. Now, if you were running a network that was fully connected for every single layer, then that wouldn't work because there's no work queue to work from. There's only one processing step. But for most of these applications, if you're running convolution, you have a work queue that you can use.
Going back to programming the weights, is the usage model such that for every usage of one of your devices, there's a training exercise to program the weights, or is it typically done in a batch where a particular customer would have the same weights for every product in the line? Because I would imagine programming the weights would be
Yes, so programming the weights takes about a minute for our chip, and so you don't want to switch applications very often. The training is done offline, so you'll have like a cloud cluster that you're doing training on using like TensorFlow, and then you have a plugin from us that has like models of the analog compute, so you'll do some fine tuning for analog and quantization. You'll generate a firmware, and then that firmware gets distributed to all of your devices. You can do on-device learning, but we haven't, at this point, fully explored that space. Because let's say you're doing like a camera system that is trying to detect very nuanced changes in the environment. You'll need to adapt to the environment, for instance. And so you'd have to do some retraining on chip. So he asked, how did we arrive at 1 million weights for an array? And it was a combination of factors. So the array is like 1,000 by 1,000. And if you look at the way that the energy breaks down for our system, these DACs and ADCs, the energy that they draw is relatively static. And so the bigger the array, the more energy efficient it will be. So that's why you don't use, that's part of the reason why you don't want to use analog compute for small problems. It only works for big problems because you get the amortization effect of the ADC. So we want to go as big as we can. And if you look at ResNet 50, for instance, many of those layers range in the around 768 weights for 768 inputs. And so if you have an array with 1,000 inputs, you've got good utilization out of those thousands. On the high end of ResNet 50, I think it was maybe like 2,000 to 4,000 inputs. And so in that case, you can use multiple arrays. You kind of break the problem up across multiple arrays. I'd say that if you look at neural networks, typically the number of inputs is on the order of 1,000. So that's why we chose 1,000 inputs, and then we made it square, basically.
You mentioned that the analog power is still in the order of 50%. 25
Yes.
What's the main? Is it in the ABCs or like it's also inherently important to the voltage, right? How low can you go down with the voltage? Is there any limit, or is it in the ABCs?
That power is largely in the ADCs.
Okay. So you go down with the voltage for the driving like a lot, or
Yeah, I
is it
mean,
not necessary?
yeah, you have that voltage across the flash transistors here, and you have a trade-off. The smaller you make the voltage, the higher the resolution you have to make your ADC. So you can reduce the voltage, you reduce the amount of current you're drawing, but then you're increasing the resolution requirements on your ADC. So it's kind of, it almost cancels directly.
Yeah. You go to slide 27, please.
Yeah, so here, if I understand correctly, there's a digital word that selects an integer number of currents that get added up. So that output current is an integer multiple of the unit current. And in that sense, it's like a quantized signal, a discrete value. But that's in sharp contrast to an actual analog signal, which is continuous in value. So can you explain how this is, why you call this analog computation?
So the question that was asked is, since the inputs to this system, and this is also true for the other system, are digital, all of the numbers are quantized. So why do we consider this an analog system instead of a digital system? So the reason why we consider it a analog system is because although the currents that are being generated are some multiple of a unit current, we're still designing op amps. We're operating in the current domain. We're generating voltages, and we have ADCs. And so this is a stark contrast to what people would normally consider a digital system, where you have full swing voltages and everything is self-rectifying and you have perfect accuracy. So we actually have to deal with noise in this system, not just quantization effects. Does that answer your question?
Is Mac the only way to do this AI?
I'm sorry?
Is Mac method doing is the only way to do AI?
So the question is the multiply accumulate operations that we're doing fundamental to AI? So there are other types of AI applications, let's be specific, machine learning, other than neural networks. But typically, you're always operating from this fundamental principle that you're trying to recognize something from a pattern. And so, as I mentioned earlier, when we're doing GPS, we're doing like that CDMA process. We're taking a input pattern that we know that the satellite's broadcasting, and we're comparing what we measured from our RF front end against it in different points of time. So we're taking that pattern and we're multiplying it against our signal to see if we find that pattern. And so any sort of recognition application, regardless of the way it was taught, neural networks or k-means or what have you, they always have this fundamental thing where you're comparing patterns against data. And so this multiply accumulate operation and these matrix multiply operations, they're fundamental to AI because it's just a pattern matching application.
And are your systems deterministic in the sense that if I have the same device, they always yield the same result on the same image, or whatever the inputs are?
So the question is the system deterministic? The answer is not entirely. So it'll be within a tolerance. So when you run the compiler, it kind of gives you estimates of what your variation is going to be. There is noise in the signal chain, and that noise is going to affect the result. But similar to the example with the GPS, the noise that's introduced by the analog is significantly less than the noise introduced from other places. So for instance, when you quantize the problem into 8-bit numbers, that actually adds quantization noise. And the power of that quantization noise is higher than the power of the noise from our system. Typically, you're using a camera system to work with our stuff. And cameras themselves have noise in the pixels. So even if you hold the camera perfectly still and you're running into a digital system, you'll still get variation in your result and the output just because the noise or the pixels are like flickering a little bit. And then the other aspect is the camera can have like different angles. So I think I saw this example where they had like a Coke bottle and they're moving the camera around and the camera didn't get any closer or farther from the Coke bottle. But since it was a different angle, the confidence that the system gave ran from like 60% to 97% just from like orientation. So from what we've seen, the analog is not deterministic, but the analog noise is so small compared to real life that it doesn't matter.
Do you guys have any concern about aging of those flash transitions as the chip is out there for longer? Can the weights change as the device ages?
So the question is how do we, will the aging of the flash transistors affect the system performance? And so what happens currently is we actually refresh the weights on a regular basis. And when we refresh, we're going to tune out any process variation in the devices because the iterative pulse programming scheme that Laura mentioned, we're actually going to set the cell to a particular value. So you could like change the mobility by 2, and it's still going to get the right value because it's a closed loop system. So that will compensate for process variation, and it compensates for effects like aging. Also compensates for things like voltage, in case you had a difference in your power supply, something like that. We have 4 minutes left, so you guys have to come up with a few questions.
Which problem do you use?
We use Mie Fujitsu plug-in flash. Yes. So they're actually about to be purchased by EMC.
Right, yeah, we use a different level of storage.
Can you repeat the question?
I think the comment was that you'd use only like full level storage in like embedded flash. So yes, we do operate these differently, and that does change our expected aging characteristics too. We're not programming as strongly. We use a smaller range of threshold voltages, and we do have 256 discrete levels.